Let's take a look now at section 4.2 about exponential functions. Now, we're going to begin with a bit of a visual example. Let's start off with a penny. Now, a penny is not worth very much. In fact, it's worth 1 penny. But we're going to go ahead and make this money grow. We're going to double the amount of money that I have. All right, well, that's another penny. And, well, that's not very much more, right? In fact, that's exactly 1 more penny. But let's say we keep doing this. Well, if I double this again, I go from 2 pennies to 4 pennies. If I double that again, I go from 4 pennies to 8 pennies. Now, if I go through and double that, well, now I'm going to end up with, well, let's see, double 8 would be 16. And from a single penny, you notice that the numbers are starting to get a little bit bigger. If I then take that and double that, well, I'm not going to take time to line them up. We end up with a whole lot of pennies. We end up with 32. Notice that by doubling the amount that we have, the number gets pretty big reasonably quickly. If we were to extend that significantly further, we have the following table that summarizes that information. So just like before, we started off with a single penny. Now, after 1 replication, right, we had 1 penny. After 1 time doubling it, we now have 2 pennies. Doubling it a second time, we now have 4 pennies. If we double that a third time, we have 8 pennies, then 16, then 32. And that's where I stopped. But look what happens if you keep going. If you double it again, double 32 is 64. Double 64 cents, that's $1.28. And if we keep doubling, we get $2.56, $5.12, and $10.24. After doubling just 10 times, we start off with 1 penny and end up with just over $10. If you keep going, you'll notice that your numbers get ridiculously big very, very quickly. Double again gets you $20.48, then $40.96, $81.92, $163.84, at $324.86, $655.36, and $1,310 with 74 cents. Now we start going higher. We start going into the tens of thousands. Here we have 2,621.44, 5,242.88, and after just 20 replications, after doubling it 20 times, we went from a single penny up to $10,485.76. Notice how quickly something grows if you double it at each stage. Here, since you don't want to hear me read a bunch of numbers to you, you can see what these are. But if you keep doubling 10 more times, from 20 to 30, you go from 10,000 to just over 10 million. Right? This is an example of what we call exponential growth. Right, so let's start off with the definition here. Definition. Let b be a constant real number such that b greater than 0 and b is not equal to 1. For all real numbers x, a function of the form f of x equals b to the x is an exponential function of base b. So that's what we're defining, an exponential function of base b. All right, so now note that usually whenever we have something raised to a power in a function, usually we have the variable is the base and the power is a constant number. So usually we have things that look like f of x equals x squared, or f of x equals x to the third, something along those lines. But these wouldn't qualify as exponential functions, because notice, an exponential function has this as just a regular constant number, and the power is what should be a variable. So here, these are not exponential. They have exponents, but that does not make them exponential functions. What makes a function exponential is if you have a constant in your base, so f of x equals to 2, and then the power should be variable. So f of x equals 2 to the x, and here g of x equals 3 to the x. Things like that. That would qualify as an exponential function. Now notice we do have a couple of restrictions here. We want b to be greater than 0, and we don't want b to equal to 1. Let's talk about this part first. We don't want b to equal to 1 because notice what happens. If b is equal to 1, then we have 1 to the power x. But then that's always just the number 1. 1 to the power 1, 1 to the power 2, 1 to the power 3. Anytime you have 1 to a power, you're going to end up with just 1. So that's not really an exponential function. It's just a constant 1. We also don't want b to be negative or equal to 0. Well, we don't want it to equal to 0 for the same reason we don't want it to equal to 1. It's boring. If b is equal to 0, 0 to the first, 0 to the second, 0 to the third, it's always just 0. But what about the negatives? Well, the negatives run into a different problem. Note, the base should not be negative. Because let's see what happens if you do have a negative base. You have f of x, for example, equals to negative 2 to the power x. Okay, so what's the problem? Well, notice, for a function to be exponential, we must have for all real numbers of x. This must be how we define our function. So here I should be able to plug in any number I like. And say, okay, plug in some numbers. Let's see what happens if I plug in some numbers. If I plug in x is equal to 0, for example, I could say, well, negative 2 to the 0, that's 1. And let's say I plug in a positive number. Let's say I plug in the number 1. All right, well, negative 2 to the first power, that's negative 2. And if I plug in a negative number, well, negative 2 to the negative 1, that's the reciprocal of negative 2, which is negative 1/2. And you say, oh, so what? That's fine. There's nothing wrong with that. Well, look what happens when I try to plug in a number that's not an integer. If I try to plug in 1/2, that's going to give me negative 2 to the 1/2 power. But remember, a 1/2 power is the same as the square root. So here, this would be negative 2 to the 1/2, which is the same as the square root of negative 2, which is an imaginary number. So here, if you have b as a negative number, if you have b as a negative number, if your base is negative, then that means that sometimes you're going to end up with real numbers, or sometimes you'll end up with imaginary numbers. And although there's nothing wrong with an imaginary number, that's not something we're dealing with. In this class, we only deal with functions of real numbers. Right? We're not trying to deal with imaginary numbers. So here we're going to exclude any cases where b is less than 0. So there we have it. We want only positive numbers for our base. And again, we don't want to use the number 1 because that would just make everything boring. All right. So now let's take a look at some examples of graphing some of these functions so that we can see exactly what they look like and look for some of their characteristics. So here I'm going to go ahead and use these two. I'm going to take 2 to the x and 3 to the x. So my very first thing I'm going to do is I'm just going to graph. Now, the very first couple of graphs that I make, I'm going to do the old-fashioned way, meaning point by point. I'm going to plug in some points, connect the dots, and see what happens. However, once we do that a couple of times, we'll start to notice a pattern which will make future graphs a lot simpler to make. But for the first ones, we're going to go ahead and graph f of x equals 2 to the x. And here we're going to do it the old-fashioned way. We're going to plug in some numbers into our function. All right, so let's go ahead and plug in the number 0. I'll plug in a few positives, and I'll plug in a few negatives. All right, so if I plug in 0, 2 to the 0, well, anything to the 0 is equal to 1. In fact, let me write that. 2 to the 0 is equal to 1. Now, if I plug in 1, that's 2 to the first power, which is 2. And if I plug in 2, 2 to the second power is equal to 4. Notice that's following the pattern of our doubling pennies, right? 1 penny becomes 2 pennies, becomes 4 pennies. If you double that again, that's going to become 8 pennies. And sure enough, if you make x equal to 3, 2 to the third power is equal to 8. So this is the equation that models the very first example that we saw with the pennies that kept doubling. If I plug in negative numbers, let's see what happens. 2 to the minus 1. Well, whenever you take a negative power, that's going to form a reciprocal. So here that's going to be the same as 2 to the first power underneath the number 1. 1 over 2 to the first, which is 1/2. 2 to the minus second, well, that's going to be 1 over 2 to the second, which is 1 over 4. Notice 1 is right here. 2, 1/2, 4, 1/4. This one's 8. What do you think this one's going to be? If we take 2 to the minus 3, that's going to equal to 1 over 2 to the 3, which is 1 over 8. And look, it's the reciprocal of this one. This is a nice pattern. If you think of that one being in the middle, everything away from those are simply reciprocals. If you raise to the first power or minus first power, second power minus second power, third power minus third power. So I can go ahead and graph this. I could go ahead and graph this by saying, notice I don't have any negative y values here, so I'm not going to worry about negative values. Here, these are all positive, and I have 1, 2, 3, 1, 2, 3. So that's negative 3 over here. That's positive 3 over here. Of course, my graph does keep going, but I'm just going to graph the first few. And let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, if I graph the points here, when x is equal to 0, y is equal to 1. All right, very nice. That's our, what would that be? That would be our y-intercept. If x is equal to 1, y is equal to 2. If x is equal to 2, y is equal to 4. Oh, that should be 2. If y is equal to 1, let's see. Yeah, if x is equal to 1, y is equal to 2. If x is equal to 2, y is equal to 4. And if x is equal to 3, y is equal to 8. If I plug in some negative numbers, if x is equal to negative 1, y is equal to a half. If x is equal to negative 2, y is equal to a quarter. And if x is equal to negative 3, y is equal to an eighth. All right. If I connect these dots, I end up with a graph. Here, ignore this one. That was a mistake. And we end up with this graph. Okay. A couple things to notice about this graph. First of all, notice that here, this number keeps getting smaller. So the line is going down as I move to the left. But also notice that it will never, ever be negative, right? Because here, if I have a positive number, notice what happens every time I take one step back along the x-axis. Here, I start at 8. If I take a step back, that gets cut in half. That's 4. If I take another step back, that gets cut in half again, and that's 2. Half of that is 1. Half of that is a half. Half of a half is a quarter. Half of a quarter is an eighth. So notice, every time I take a step to the left, my graph gets half as tall. But notice, if I take half of 1/8, that'll be 1/16. And if I take half of that, that'll be 1 over 32. And no matter how small it gets, there's always going to be a little something left. If you have a very tiny number and you cut it in half, you're going to get an even tinier number. But it's still not going to be 0. There's still going to be something left. So here, your graph will get smaller and smaller and closer to the x-axis. But since it's never going to be 0, since there's always going to be something left, then it never touches 0. And as we saw in the previous chapter, whenever you have a graph that gets closer and closer to a line without ever touching it, that's called an asymptote. So one thing to note here is that your function has the x-axis as a horizontal asymptote. So here the x-axis is a horizontal asymptote. Okay. Notice I don't have any x-intercepts because, of course, my graph doesn't touch the x-axis since that's the asymptote. But I do have a y-intercept. That was 0, 1. 0, 1. And there we go. Notice that the pattern of this graph does follow the same pattern that we saw with the example of the pennies. Here, if you take one step forward, the height will double. If you take another step forward, notice the height doubles again. This goes from half a line to 1 line, from 1 line to 2 lines, and if I double that again, instead of 2 lines, that goes up 4 lines. Every time I take one step forward, the height of my point gets doubled. Likewise, every time I take a step backwards, the height of my point gets cut in half. So now let's consider a similar graph, and I'm going to do these side by side. Example, let's go ahead and graph f of x equals 3 to the x. All right, so I'm going to do this again the old-fashioned way. I'm going to just plot a few points. Here's x and here's f of x, just like that. And now I'm going to plot a few numbers. I'm going to say, okay, let's plug in 0 and 1 and 2 and -1 and -2. All right, let's see what happens there. Well, again, if I plug in 0, 3 to the 0 is equal to 1. Notice 0, 1 happens on both cases. Well, that's always going to happen because it doesn't matter what your base is. Anytime you raise something to the 0, you get 1, which means that if I have 2 to the x or 3 to the x or 4 to the x or 20 to the x, it doesn't matter. 0, 1 will still be a point on your graph. All right, let's plug in a few other numbers. 3 to the first power is equal to 3. 3 to the second power is equal to 9. If I have 3 to the -1, that's 1 over 3 to the 1, which is just 1 over 3. And if I have 3 to the -2, that's 1 over 3 to the 2, which is 1 over 9. Oh, has the same pattern as before. If I consider this one to be in the middle, everything to the right of that is just the reciprocal of everything to the left of that. 2, 1/2. 4, 1/4. 8, 1/8. Over here, 3, 1/3, 9, 1/9, and so forth. All right, so let's take a look at the graph of this thing. All right, I still have 0, 1, but all my other points are different. 1, 3. Okay, so if I go to the right one, I'm going to go up 1, 2, 3. Hey, that point didn't go to waste. All right. If I have 2, 9, I'm going to go 2 to the right and up 1, 2, 3, 4, 5, 6, 7, 8, 9, just like that. But if I go to left by 1, I'm going to go down, I'm going to go up 1/3 of a point. Notice that's not even as far as I did before. And if I go to the left by 2, I'm going to go up 1/9. And if I connect my dots, you'll notice that I have pretty much the same kind of shape. Yeah, it's going through different points, but it has the same kind of shape. This graph in red and this graph over here in blue, even though they are going through different points, exhibit a lot of the same features. Those features are the features that you'll find on any function that looks like a number raised to power x. So those features are as follows. So let's take a look at properties of the graph of f of x equals a to the x. Okay? Here we're going to say a is a positive number. Now note that your graph is the graph of an exponential function, and we've said that exponential functions have to have positive bases, and their bases should not equal to 1. What I'm going to do here is I'm going to split this apart and say, well, okay, my exponential function must have a base that's positive and not equal to 1. Let me consider what happens if b is greater than 1 and compare that to what happens when b is less than 1. We'll see that here. So for right now, I'm going to take a look at the properties of the graph of a to the x where a is greater than 1. Right? We'll take a look at what happens when a is less than 1. Of course, it still has to be positive, so between 0 and 1. We'll look at that separately. So whenever you have the graph of f of x equals a to the x, the y-intercept is going to be 0, 1. Right? We see that in these graphs here, that whenever x is equal to 0, y is equal to 1. We also see a horizontal asymptote. So another property is that the x-axis is a horizontal asymptote. Okay. The other thing is notice that the graph will follow the asymptote, but it'll only follow it this way. It doesn't follow it on both directions. It only follows it to the left. To the right, it goes up higher and higher and higher. So here, the x-axis is a horizontal asymptote. The graph follows the horizontal asymptote only on the left side. While on the right, it grows. is going to get taller. Not only does it get taller, but it's going to get taller in a predictable way. Notice here, if my base is 2, every time I take a step forward, my height doubles. All right, so here I go from 1 to 2. Double 2 gives me 4. Double 4 gives me 8. Over here, this base is 3. Well, I started off with 1, but if I take a step forward, my y value triples to 3. If I take another step forward, my y value triples to give me 9. So what this base is telling me is every time I take a step to the right, my graph will get this many times taller. So that's another property. Every time you move one step to the left, not to the left, to the right. Every time you move one step to the right, the graph will get will be a times as big. And finally, our domain and range. The domain of every one of these, notice, is infinite, and we kind of get that by definition. Our definition says for all values of x. Well, x is what you're plugging in, so that's your domain. So here this must be true for all values of x. That means there is no restriction on the domain. The domain is from negative infinity to infinity. But notice that your range is not going to go on forever in both directions, because here, no matter which one of our graphs we had, we saw that the x-axis was a horizontal asymptote, and we saw that the graph stays above that horizontal asymptote. So the range is from 0 only going up. So our range is from 0 to infinity. Notice we don't ever actually reach 0, right? We stay just above the line, and so the range is from 0 to infinity with round parentheses on both. Every time we see an exponential function with a base that is bigger than 1, the graph looks pretty much the same every time. This is going to be the point 0, 1. Here I'm going to have the x-axis works as an asymptote. The graph will be flat on the left, and it'll grow up on the right. So right here, if someone told you, hey, sketch the graph of 2 to the x. Well, there it is. Oh, I'm sorry. I meant sketch the graph of 3 to the x. Yeah, that's it too. Oh, I mean, sketch the graph of 40 to the x. Yeah, that's it right there. Every exponential function looks like that. Now, obviously, the specifics are different. Right? They have different points with different numbers, but the sketch is exactly the same. Every one of your exponential functions will look like this as long as your a is greater than 1. This is called an exponential growth function. And that's what happens whenever you have a function that is exponential and its base is greater than 1. The name is about as straightforward as we can manage here. It's exponential because that's the type of function you have. It's an exponential function, and here growth means that as you move from left to right, it's growing, it's getting taller. Now, what happens if you have a being less than 1? Well, it turns out that not much changes. Let's take a look at properties of the graph of f of x equals a to the x, where a is less than 1. Let's take an example. Let's go ahead and sketch the graph, and I'll go ahead and do this down here so that we can write up the properties up here together. I'm going to go ahead and sketch the graph and I'm only going to do one. Let's go ahead and graph f of x equals 1/2 to the power x. Okay. All right, so I could do this the simple, old-fashioned way and just plug in some numbers and see what happens. All right, so let's see. If I plug in 0, if I plug in 1 and 2 and -1 and -2. Now, of course, one thing we could do is, which I haven't done, we can plug in fractions into all of these. Notice up here, we couldn't plug in a fraction because that would give us an imaginary number, and that would cause problems. But here, I can take the square root of 2, I can take the square root of 3, I can take the square root of 1/2. The problem is that that's just not something that's easily accessible. That's not something we can easily come up with a number, and since we're not allowed a calculator in this class, well then that's not something we can realistically do in a short amount of time. So here I'm picking integer values, but keep in mind all of these could be done with fractions and decimals and everything else. After all, this is a continuous graph. It goes on, which means that everything in between these points is also part of your function. So anyway, 1/2 to the power 0, well again, anything to the power 0 is equal to 1. 1/2 to the power 1, well that's a half. And 1/2 to the power 2, well 1/2 times 1/2, that's 1/4. Okay, if I take 1/2 to the power -1, remember negative powers take the reciprocal of this. So this would be the same as 1 over 1/2 to the first power, or in other words 1 over a half. And dividing by a half gives me 2. Over here, if I take 1/2 to the -2, that's going to be 1 over 1/2 to the 2. But 1/2 to the second power, that's a quarter. So that's 1 over a quarter. And again, we're taking the reciprocal of a quarter. Oh, so that's 4. Notice that it's the same numbers that we had over here. 1, 2, 4, right? 1/4, 1/2, 1, 2, 4. 1/4, 1/2, 1, 2, 4. So it's got the same values as 2 to the x did. But the thing that you note here is that they are in the opposite direction. Here, your function gets bigger as your x value gets bigger. But over here, as your x value gets bigger, your function is getting smaller. If you graph that, it becomes even more apparent. So let's say I'm going to graph, and here let's just do 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. If I graph this, well, 0, 1, 1, 1/2, 2, 1/4. If I go in the other direction, -1, 2, and -2, 4. If I now connect the dots, I notice that it's the same graph that I had before, but reflected. Notice that over here, I have this function. It's still doing the same thing. Every time I take a step, it's doubling the value. Hey, here that's a half. Double gives me 1. Double 1 gives me 2. Double 2 gives me 4. It's the same pattern with the same numbers as this graph was, but now it's being reflected. Whereas the exponential function with a base of 2 grows to the right, here the exponential function with a base of a half shrinks to the right. The way we say this is it decays. This is called an exponential decay function. So whereas this is called exponential growth, this is called exponential decay. And it has pretty much all of the same properties. Notice the y-intercept is still the same. I still cross through 0, 1. So that's exactly the same. My y-intercept, 0, 1. So you don't have to remember different ones for these. They both have the same intercept. Notice they also have the same asymptote. They both get close to but don't touch the x-axis. So here I have the x-axis is a horizontal asymptote, just like it was for the previous one. But now the difference is here, the horizontal asymptote, you follow it to the left, whereas for the decay function, you follow it to the right. So that's the main difference. The graph follows the horizontal asymptote only on the right side, while on the left it's going to grow. Here, every time you move one step to the right, hey look, this started off as 4. I take a step to the right, that's now a height of 2. Now if I take another step to the right, that's a height of 1. And if I take another step to the right, that's a height of a half. So every time I take a step to the right, I'm cutting this in half. Well, yeah, but that's what the base was. The base is telling you every time you take a step to the right, you're going to multiply your current height by that. That's exactly the same thing that the previous function did. Every time you move one step to the right, the graph will get a times as big. In this case, half as big. And finally, the domain and range, you notice, are the same. This goes forever left and right, but up and down, it starts at 0 and only goes up. So my domain is still from negative infinity to infinity, whereas my range is only from 0 to infinity. And this is called the exponential decay function. I can sketch the graph of every exponential decay function just like this. They all cross through the point 0, 1. They all have the x-axis as a horizontal asymptote. They all go up to the left and flatten out to follow the asymptote as you go to the right. This will happen anytime you have a less than 1. Now remember, your base still has to be greater than 0. So when we say a less than 1, we mean something between 0 and 1. So here, this means between 0 and 1. So if, for example, I say, all right, we're going to go ahead and sketch the graph of 1/3 to the x. It'll look like that. Oh, I'm sorry, I meant 1/8 to the x. Yeah, it'll look like that. Oh, I meant 2/5 to the x. Yeah, it'll look like that. In fact, any number, as long as it's between 0 and 1, if you take that number to the x, it'll give you this graph. But now if you look at these functions here, and depending on how you think about them, you could think of these as two different graphs, or you can think of them as two versions of the same graph. After all, there's just a reflection. But however you want to think about them, here you have a basic shape which has a few basic properties across every instance of it. But we've seen something like this before. If you think back to chapter 2, that's what a parent function was. A parent function was a basic graph of a basic kind of function, which we could then modify to create graphs of more complicated versions of that function. So guess what? We're back in chapter 2, and we're going to be looking at graphing these things. And instead of graphing them point by point, which we've seen can take a bit of effort, especially if your numbers are not very nice, we can graph these using the concept of a parent function. So as an example, let's go ahead and look at creating the graph of this. Let's sketch the graph of f of x equals, let's pick a nice pretty number here. I like the number 7. Why not? Let's do 7 raised to the power x minus 2, just like that. Let's start with that. All right, so remember your modifications, your transformations of your parent function. If you have f of x is the parent, then if you have f of x plus c, that's going to move everything to the left by c. If you have f of x minus c, that's going to move everything to the right by c. If you have f of x and then outside of the function you add c, well then that's going to move everything up by that amount. And if you subtract from the function, that's going to move everything down by that amount. Okay? These were our translations. And translations don't change the shape of the graph, they only change the position, up, down, left, or right. We also had reflections. And reflections were caused by a negative. If you have a negative on the outside of your function, that's going to cause everything to flip upside down. On the other hand, if you have a negative on the inside of your function, then that's going to cause a reflection not upside down, but left to right. We also had dilations, which were caused by multiplying by a number. But in this section, we're not going to be looking at dilations, so this will be enough. Now, this function, we have a parent function. Remember, the parent function is the most basic version of a function without any additions, subtractions, multiplications. Just the simplest version of an exponential function. Well, that looks like a number to the power x. So here, this parent function, I'll call it p of x, p for parent, would be 7 to the power x, which means everything that's different from this function to this function is caused by a transformation. So here, the only difference between this and this is this minus 2. Now notice, that minus 2 is not to the whole function. It's not 7 to the power x and then minus 2. I'm only subtracting from the variable, only subtracting from the x. So over here, that's going to look like this. I'm subtracting a number, but only from the x, not from the whole function. Oh, well, if I'm subtracting a number from just the x, that's going to move everything to the right by that many units. So here, this is going to cause me to move everything to the right by 2 units. All right, so let's start by graphing our parent function. The graph of the parent function is very, very short and simple because we know that it looks like one of these. It's either going to be the exponential growth function or the exponential decay function, and the difference comes from, is your base bigger than 1 or less than 1? Well, in this case, 7 is definitely bigger than 1, so it's going to be an exponential growth function. So that'll be our parent function. So let's start off with that. Let me do this in pencil here. So here's my exponential growth function. And it'll look something like that. All right. Here, I'm going to keep track of that point. This is the only point that I really know for sure without actually graphing a bunch of details. It's the only point that's common to every exponential parent function, whether it be growth or decay. So now if I'm going to move everything to the right by 2 units, well, that's going to take this and it's going to move it over to the right 1, 2 units. Now notice, I have a horizontal asymptote. But if the horizontal asymptote is the x-axis, if I move the x-axis to the right, well, it's still the x-axis. So the asymptote hasn't really changed. This is still going to be the horizontal asymptote along the x-axis, but what has now changed is this point. So now I have this exact same graph with that same shape, that same orientation, everything about it's the same, except everything about it moves to the right by 2 steps. So now instead of 0, 1, this is now 2, 1. And I can now redraw the same graph shape in its new location. And there we go. This is now the graph of f of x. Here, I went ahead and used pencil for p of x. And there we go. Let's take a look at another example. I'm going to leave these right here. Another example will be, let's go ahead and sketch the graph of, we'll say f of x equals to, let's say 2/3 raised to the power x minus 1, and then I'm going to say plus 1. Like this. So give this a try. Pause the video for a minute and give this a try. Start by graphing whatever your parent function is, and then whatever modifications are caused by either your translations or reflections, you're going to go ahead and graph those as well to give you a result. So pause the video and give it a try. All right, so let's take a look and see what this graph will look like. So we're going to start off with the parent function, and our parent function is the base to the power of x. All right, so let's go ahead and write that out. Parent function is going to be p of x equals to, here my base is 2/3. So let's write that as 2/3 to the power x, which means that anything that is different from this to this is causing a transformation. So here I see two differences between my parent function and my final result. I have a -1 right here, and I have a +1 right here. Notice that the -1 is causing a change to only the variable x. Well, that'll look just like this. Here, I'm subtracting a number from just the x, and that's going to move everything to the right by that many steps. So here this one's causing everything to move to the right one step. Here I have a +1, and notice that's not just to the x. I'm adding that 1 to everything here. So that's +1 to the entire function. Okay, so that's going to move everything up by a step. All right, so I can now graph this. I'm going to begin with the parent function. And again, every exponential parent function crosses through the point 0, 1. But now notice this is got a base of 2/3. And since 2/3 is less than 1, this is going to be the exponential decay parent function. So here, I'm going to start with the parent function. It's going to go up to the left and down to the right. Keep in mind the x-axis is an asymptote. All right. So now, -1 right here causes me to move one step to the right. Okay, so that's going to move one step over to the right. So now instead of having this point being 0, 1, and it's a nice thing I use a pencil here so I can get that out of the way, 0, 1. If I move everything to the right by one step, that is now the point 1, 1. I'm going to still draw this in pencil because that's not my final answer. I have one more transformation to do. So here I'm going to say I have the same graph. It's got the same shape, same size, same orientation, but the difference is now it's all moved over to the right. Okay. Now, the next thing to do is I'm going to move everything up one step. Notice that if I take the x-axis, which is the asymptote, and I move everything to the right, well, that's still the same asymptote. It's still the same x-axis. If I take a horizontal line and I move it, it's still a horizontal line. But now if I move things up, well this, if I take the x-axis and move it up, that is no longer the same line. If I take this line and move it up one step, that means I now have a new asymptote. So, whereas before my asymptote was the x-axis, my new asymptote will be up here. It'll be the line y equals to 1. All right? I'm moving everything up one step, so that's going to cause this asymptote to move up one step. Likewise, this point, 1, 1, will also move up a step. Okay, so that's now instead of 1, 1, that's now 1, 2. And now I have this shape, the exponential decay graph, but now, instead of crossing through that point and having this asymptote, now it crosses through this point and has this higher asymptote. So it doesn't reach the x-axis anymore. Now it only reaches down to this red line. And this is my function. This is my f of x. And there we go. The last thing we're going to be looking at is this right here. Saying, well, what is that? It's the letter E. Well, E represents a number. Okay, well, what number does it represent? And why don't you just write the number the way you usually write it? Why don't you write 5 or 6 or something like that? Well, because E doesn't represent a number that's easy to write down. It represents a number that's approximately 2.7. And you say, well, 2.7 is not that hard to write down. Well, no, but it's not 2.7. It's in fact much longer than that. It's 2.71828 1828 ... It keeps on going. So so this number right here, e, is kind of like pi. Right? Pi is a number that keeps on going and going and going, and it's not an easy number to write down. 3.14159265535, so forth and so on. Well, we don't want to write down that entire number, so we have a symbol that stands for that number, the symbol for pi. Same thing here. E is a number that's approximately 2.7. Now, unfortunately, because in this class we're not allowed a calculator, there's going to be a few things that we're not going to be able to see in full. In particular, a lot of our applications in this section, in fact, in this whole chapter, can't really be done in a reasonable amount of time if you're doing them manually. Since we're not allowed a calculator in this class, then we're not going to be doing most of those applications. So, for now, this number e is just a number. Right? To see it in full, to see some of the more important details about it, we would have to do some stuff that is just not accessible to us right now. So for us, this is just a number. Now, that's not to say this number is not important. It's just something we can't really see the importance of too much right now. Incidentally, this number has a name. The letter E stands for Euler, and this is Euler's number. For those of you who go past college algebra to eventually get to calculus, Euler's number becomes significantly more important there. Also, it becomes important in a few other places of application, in particular in chemistry, in physics, and maybe a little unexpectedly, in finance and economics. The reasons for that being exponential functions play roles in all of those fields. But for now, this is just a number. So we could give one more example. And we could say, let's go ahead and sketch the graph of f of x equals to e to the power of negative x plus 1. All right. Now, that looks a little strange. Right? Normally, we have a number there, some number to the power x. But you know what? This is a number. 2.718, whatever. It's a number. So it can be graphed just like every other exponential function. Notice that this number is in fact greater than 1. And so my parent function, which is e to the x, parent function is e to the x. And since e is a number that's about 2.7 something, well, that's definitely greater than 1. So, since my base is greater than 1, my parent function is the exponential growth function. Yeah, that number is a little more complicated than some of the other numbers we've seen, but the parent function is still the same. Here, since e is greater than 1, this exhibits exponential growth. So we can go ahead and graph this thing. I have my exponential growth function. Okay, well that's going to be my parent function. Just like every exponential function, every exponential parent function is going to cross through 0, 1, 0, comma 1. And it's going to have the x-axis as an asymptote. Since it's growth, it's going to grow to the right, and it's going to shrink down to the left, just like that. Okay? So now everything that's different from the parent function to the function f is causing a transformation. So here, the two differences that I see a minus right there, and I see a plus 1 right there. Well, going back up here, whenever you have a minus, the minus can either appear on the entire function or on just the x. So here, take a minute, pause the video, and graph it. See what you can do. And then we'll go through it together. All right, so now let's take a look at this. If you have e to the minus x plus 1, all right, well that minus x, that's a reflection, and since the negative is just on the x, the reflection will be left to right. So this will reflect left to right. This plus 1, notice that's a plus 1 on the entire function, not just on the x. I'm not just adding 1 to the x, I'm adding 1 to everything. So that's going to move everything up by 1 step. Okay, so I can perform both of those transformations. Here, I'm going to reflect everything left to right. So everything that's to the right of the y-axis is now to the left. And everything that was to the left of the x-axis is now to the right. Okay? So this was my parent function, p of x. This is a reflection across the y-axis because of the negative on the x. And now plus 1, well, just like before. If I have the x-axis and I reflect it, well, now that's still the x-axis. Right? It's flipped around, but it's still the same line. But if I take the x-axis and move it up, well, that does change things. So now if I'm moving this up, my asymptote is different now. Instead of being the x-axis, now it's up here, 1 step above the x-axis. That's going to go up 1 step, horizontal asymptote, goes up 1 step. And now, this point would also go up 1 step. Right? So now, instead of having an intercept at 0, 1, I now have one at 0, 2. And now I have this function right here. Remember, it's been reflected. This was my parent function. This is the reflected one. So this is the one that's going to move up that 1 step to 0, 2. So that's moved up 1 step. Remember, it's no longer following the x-axis. Now it's following this new asymptote. And so this right here is the graph of our function f of x. All right. So that is it. That is it for this section. And I hope you all have a nice day.